All right, and we are back to it, my friends. So we're going to continue with our work with tables, all right, and writing equations of functions. And this time we're going to look at two more functions. We're going to look at a quadratic function or exponential function. We looked at linear and absolute value last time. So this is standard 6.3. I can write the equation of a quadratic function from a table of values. Now, once again, with both of these functions, just like we did last time, we're going to try to connect it to some things that you should already know. So let's start with all right, our equation of a quadratic, y equals a times the quantity x minus h squared plus k. All right, and I'm going to start with the hk because this is just like what we did with an absolute value, right? So the hk is our vertex, right, or turning point, just like what we did last time. All right, so we identified that at the same way, excuse me. Now, the a value is what's different. And this is maybe where you don't remember the pattern. So I'm going to give this to you, and hopefully as we look at our quadratic and we look at their tables, all right, this will come back to you. So our a is actually equal to the rate of change divided by 2. All right, a is equal to the rate of change divided by 2. All right, so just like we did last time, what I want you to do is pause the video, write the equation of this quadratic, all right, from the table, flip the video back on, and we'll see how you did. All right, so let's start with the vertex. We know the vertex is 4, -5. So I really already have the problem halfway beat, all right, if I can identify the vertex. Now, what we've talked about graphically is that we saw that the a value, all right, was the first step, all right, so up to the right one, the first step in our, all right, rate of change, all right? So a is equal to 2 over 1. And that was what we were using, all right, for our a value, just like that. Okay, now we developed that based on some pattern finding. And the other part of that was that a is equal to the rate of change divided by 2. All right, so we have to know, okay, if I'm looking at it graphically, I can look at my first step in my rate of change. And I know it's got to be the positive 2, all right, because it opens up. All right, but we are not going to necessarily always see that in a table. All right, so let's jump down here. All right, and once again, let's try to transfer what we just did to our table. So once again, the first thing that we always want to try to do is just scan that table, find a turning point, because that gets us down to two functions if we see one, absolute value or quadratic. So when I look at this table, I can see there's my turning point for -5, all right? So even though it's listed as step 2 in the process, we really should do that right away to help eliminate, all right, half our choices. Now, let's do our rates of change like we've done before. So notice all of our x values, all right, all go up by 1. All right, all go up by 1. Now, 3 minus 3, or 3 to -3, I go down 6. -3 to -5, I go down 2. So what I see right away is I say I have -6 to 1 and then -2 to 1. So I have a turning point and a non-constant rate of change. So that tells me it's quadratic. All right, last time we saw the turning point and a constant rate of change in both directions, and that's how we knew it was absolute value. So right now we know this is going to be quadratic. So we know the blueprint, right? A x minus h squared plus k. All right, now let's keep going with those rates of change. -5 to -3, I get +2. We get that turning point. We should get a change, all right, in our change of direction in our rate of change. And then -3 to 3 is an increase of 6. All right, so now let's look at the pattern. From what we've done before, we should see that we have a pattern in these changes, all right, on the right-hand side. So when I go from -6 to -2, I go up 4. When I go from -2 to 2, I go up 4. When I go from -2 to 6, I go up 4. So before, when we talked about describing the rate of change, we would have said this rate of change is increasing by 4. So in our first unit, that's how we would have described the rate of change. Now, if we go back up here, one of the things that we talked about was that the a is equal to that rate of change divided by 2. So what is that? A is going to be the rate of change increasing by 4, +4, divided by 2, and that's equal to 2. And that's the same 2 over 1 we saw here. So that's the first way. Now, just like what we did graphically, notice the a value is the first change, my first step in my rate of change to the right, all right, of my vertex. Now notice, I see that in my table as well. There's that 2 to 1 that I saw in my graph. So there's actually a couple different ways to find your a value. You can always do the rate of change divided by 2, and it's always going to be this first rate of change after your turning point. And then once again, we can just take that information, 2 for my a value, x minus 4 quantity squared minus 5, and there's our equation, all right, for our quadratic. Okay, so let's flip our page here, and let's go to our group practice here. And just kind of like we did last time, we're going to do this in pieces, all right, and go back and forth. So what I want you to do is actually step 1 and step 2, all right? Find the rate of change from the table, find your a value, identify your turning point, flip the video back on, and we'll see how you did with that part. All right, did you really do it, or are you just waiting on me? No, really, pause the video. All right, do it. All right. Okay, now let's see what you really did. Okay, so once again, if you scan the table, hopefully you circled -5, all right, 8 as your turning point. And then if we look at those rates of change, increasing by 1 on the left side, all right, we go up by 9, we go up by 3, we go down by 3, we go down by 9. All right, and then we look at that pattern. Okay, we have a turning point and a non-constant rate of change that tells us it's quadratic. So that gives us our blueprint for our equation. All right, and now when I look at my pattern here, I see that these are all going down by 6. So the rate of change would be this is decreasing by 6. Now, once again, 2 ways to find the a value. One way is that it's going to be the rate of change, which is -6, right? Decreasing by 6 divided by 2, and that's -3. The other way, once again, is that first step in our rate of change to the right, just right past the turning point, right below the turning point. There's -3 to 1. All right, so y equals -3, and then x minus -5 is going to make that a +5 squared, and then +8. Now, the other thing, just like what we did with our quadratic, or excuse me, with our absolute value, you can sketch this to make sure your a value is correct as far as whether it's positive or negative. So notice I have a positive rate of change, a positive rate of change, a negative rate of change, and a negative rate of change. So that means it would have gone up, hit that turning point, and then come back down. So that tells us that our a, right, has to be less than 0 because it opens down. So you can verify the sign, all right, okay, whether it's positive or negative a value by sketching the graph just like we did with our absolute value function. Okay, we'll save 10 for class. All right, so let's flip, all right, and take a look at, all right, our exponential function. So you can see that that is standard 6.4. I can write the equation of exponential function, all right, from a table of values. Now, once again, I'm going to start with this k value, right? So we said this was the floor, all right? The proper mathematical term is that this is our horizontal asymptote, something like that. Redneck speech impediment's hard for me to say. Look at all those consonants in a row, man. They're messing with me, all right? All right, so there you go. But that's our floor. That's our horizontal asymptote. And then what we said was b, right? That was our multiplier or our divider, depending on whether we had a graph that was going uphill, it would be a multiplier, or if we had a graph that was going downhill, and then it would be a divider. All right, so just like we did a few minutes ago, all right, I want you to pause the video and write the equation of this exponential graph right here. All right, let's see how you did. So we can see, right, that the floor is +4. So I have the problem halfway beat. So there's my +4. Now, hopefully you see that our graph is going uphill. Therefore, we have a multiplier. So if I look, I go up 1, and then up 3, and then up 9. 1, 3, 9. That means I'm multiplying by 3, so my base is 3. And there's our equation. All right, so once again, transfer of knowledge, right? We want to see those same things in our table. Now, when we look at the floor, let me pull my graph back up here. You can see that the tail of our graph gets really, really close to 4. And even though it looks like it hits it in our graph, it never really does. It gets really, really close to 4, but never quite hits it. So when we look at that in our table, this is where, once again, we have some telltale signs. This is really the only time we get like kind of some quirky, funny decimals in our table because I'm getting really close to a number. So 4.33, 4.11, 4.037, 4 point whatever, right? That's when you know, like, oh, maybe this is something different because I'm getting really, really close to a value without touching it. All right, so in this case, we can see that my floor would be +4. Now, that floor could be at the top of the table. It could be at the bottom of the table. So you're just looking for those decimals and seeing if it's getting closer and closer to a number. Now, we want to find our multiplier. Well, that's kind of hard sometimes because we have these decimals. So what you might want to do is, all right, ignore some of the decimals and go to some of the other numbers you might know. So 4.33 to 5, that went up 2/3. 5 to 7, that went up 2. Oh, I should have done all my x's over here. Got a little hurried there. All right, so all of our x's are going up by 1. Notice, and I just totally goofed this up because I just kind of got so excited about the floor there. I totally jumped, right? We didn't look for a turning point. There's not one. All right, and then I got so excited I didn't consider my change in x. So don't be like me. All right, don't be in math there like me. Take your time. Be a little bit bored with it. It's okay. All right, and then get it to everything in the right order. All right, and now if I go back here, I can see that this goes up 6. So I have no turning points, a non-constant rate of change, so I know it's not linear, I know it's not absolute value, and so where I get down to is like, is this quadratic or is it exponential? And notice they're not increasing by the same amount, which means it can't be quadratic. And so now I'm going to look for that multiplier. And this is where knowing your functions helps you. So 2 times 3 is 6. Well, 2/3 times 3 is also 2. So I can see that my multiplier is 3. And hopefully we'll give you a little bit more in the tables to make that a little bit more clear for you. And then once again, we just take that information and write it into our equation. All right, let's do one more problem together. So let's look at the group practice number 11 here. All right, and once again, I'd like you to pause the video and find your b value and your k value if you can, and then we'll write that equation. All right, I'll give you guys a few minutes to do that. You pause the video, flip it back on, and we'll see how you did. Okay, now let me try to see if I can get this in the right order this time. So first, scan your table to see if you see a turning point. Don't see one, all right? Now we get into the rates of change. Always consider how x is changing. And when I look at my left side, I can see all of those x's are in fact going up by 1. All right, now let's jump over to the change in y's. My first change in y, I go down 48. My next change in y, I go down 12 to 1. So right now I can throw two functions out, right? Negative 48 to 1, negative 12 to 1 are not constant values, right? They're not constant rate of changes. They're not equal to each other. So I know it can't be linear. I know it can't be absolute value. Probably not quadratic because I don't see a turning point, but we can check in just a moment. Negative 1 to 4, I go down 3. Negative 4 to negative 4.75, I go down negative 3/4. And then once again, I can see those decimals, right? Negative 4.75, negative 4.93, negative 4.98. It's getting really, really close to negative 5. Getting really, really close to negative 5, okay? So, all right, there's my k value, all right? Now, how do I know it's exponential? One, this is a really big hit, right? It's getting really, really close to a value. It's the only function that does that. Now, here's the other thing. I definitely know it's not linear. I definitely know it's not absolute value. And so to know if it's quadratic, it should be changing by the same amount every time. So I go up by 36, I go up by 4, so it's definitely not changing by the same value every time. But is there a multiplier or divider? And notice I'm going down. So that means I'm getting a divider. So 48 divided by 4 is 12. Excuse me. Negative 12 divided by 4 is negative 3. Negative 3 divided by 4 is negative 3/4. Now, since I'm dividing, remember that means I'm going downhill like this. And if you remember, all right, from what our work with exponentials, that means we need a b value between 0 and 1. All right, and so since I'm dividing by 4, that would be 1/4. All right, and so then we take that information, 1/4 to the x minus 5. Now, I didn't mention this with any of our other table work, but one of the ways you could change or check your work, all right, is if I have the correct equation, when I plug in my x values, I should generate this y value. So that's a great way to check your work when you're writing the equation from a table. So if I plug in negative 3 into this equation, I should get 59. If I plug in negative 2, I should get negative 5. So same thing over here with our quadratic. If I plug in negative 7 into this equation, I should get negative 4. So that's another built-in check that you could use, all right, to verify that your equation is correct. All right, that wraps up this part of the lesson on writing equations from tables. We'll finish the rest of this in class. See you next time.